All right, welcome to lesson 12.4 on aqueous solutions. So today we're going to look at small measurements. So for example, we'll start off with a problem here. Describe the preparation of 10 milliliters of a 0.15 molar solution of lithium fluoride. Okay, again, we need describe the preparation. We need to prepare lithium fluoride. We need to know how many grams we're going to add. We can't start with moles of lithium fluoride. We don't really have a machine in the laboratory that can measure out moles. We do have a balance that can measure out grams. So we need a mass of lithium fluoride. We need to make 10 milliliters of a 0.5 molar solution. So we'll convert milliliters to liters. That's the first step here. Then molar, again, we have to keep in mind that molar is moles per liter. So now we get the liters on the bottom, moles on top. They cancel out here. Here's how we go. Use our molar situation to go from volume to amount of material. And then something we've been doing for several months now, moles to grams. And voila, we now know how many grams of lithium fluoride we'll need to make a 10 milliliter solution of 0.15 molar lithium fluoride. Here's the issue. Our balances only measure to the nearest hundredths. So that'd be right here. We don't know if we have 3.9 or 3.8 or 3.7 or 3.6 or 3.1. We could even potentially have 3.0. We just don't know. Our balances are only accurate to the nearest hundredths, which means we're looking at potentially a 25% error. We want a molarity of 0.15. We might end up with a molarity as low as 0.11. So for this reason and other reasons, it's not always practical or even possible to measure the mass for a very dilute solution. In such a case, what we do is create what we call a stock solution. This is a concentrated solution, and we can then use that stock solution to make dilutions to our desired solution strength. So whenever we add solvent, more water, to a small amount of stock solution, we are diluting it. So the example here, we have a stock solution. We take 1 milliliter of the stock solution and then add 9 milliliters of water. Our new solution, our dilution, is now only 1/10 the concentration of the stock solution. You could repeat that process. We see here, we're going to the second test tube. Again, only 1 milliliter of the now diluted material and 9 milliliters of water, and all of a sudden we have 1/100th the strength, or 1/100th the concentration of the stock solution. If we repeat that process again, 1 milliliter of the second diluted solution and 9 milliliters of water, and now we're down to 1,000th of the initial concentration, and 1/10 of that would get us to a 10,000th. And these are dilutions that we're preparing. Another practical application of stock solutions and dilutions is if you want to make multiple solutions of the same strength. Rather than risk the error of measuring out the correct mass of particles and adding it the correct volume of water each time, you could just make a stock solution and dilute it down several times, or make several different dilutions from that one stock solution. Should end up with a much more accurate version of a consistent concentration for your solution. All right, here's some problem solving. How this looks on a piece of paper. What volume in milliliters of 2 molar calcium chloride stock solution would you use to make 0.5 liters of 0.3 molar calcium chloride solution? Boy, so we've got a lot of information here. They're telling us we have our stock, or our concentrated solution, as a 2 molar calcium chloride solution. And they want to know how much of that initial solution we need to make half a liter of a 0.3 molar solution. All right, so we're looking for a volume of stock solution. So how much stock solution, they want it in milliliters, they did specify that, to make a 0.5 liter dilution. Now you'll notice I use the term stock and dilution, DLT for dilution. Use STK if you want for stock. I think that's really, really helpful. A lot of times we're working with volumes, milliliters to milliliters, liters to liters. In this case, milliliters to liters, and they're not the same. This is a volume of dilution, this is a volume of stock. So I think it very much helps to label what volumes you're working with, and that'll help determine or help you to determine what the next step should be and when you've got your desired volume. So we're looking for half a liter of dilution, and we know that our dilution should have a 0.3 molarity. Again, we have to see molarity as moles over liters. So now our liters of dilution cancels out, and the unit that we're working with is moles of calcium chloride. Our stock solution is moles over liters. Now we've been talking about this for quite some time. I can travel 60 miles per hour, or in 1 hour, I'll travel 60 miles. It doesn't matter if I write it top to bottom, bottom to top. What matters is getting these units to cancel out. Moles calcium chloride, moles calcium chloride. So here is my 2 molar moles under liters, 1 liter per 2 moles of stock solution. And finally, convert our liters back into milliliters. Crunch the numbers and we find out we're going to need 75 milliliters of stock solution. Let's try another example. Describe the preparation of 10 milliliters of a 0.15 molar solution of lithium fluoride from a 3 molar stock solution. Okay. 3 molar stock solution. We need to know what volume of that stock solution we're going to need. So we'll start with that. Question mark, volume, stock solution. We're trying to make a 10 milliliter dilution. What's the concentration of that dilution? Again, you see the big M, you know it stands for molar, but more importantly, you know it stands for moles per liter. Excuse me, I did my milliliters to liters first. Again, molar is moles per liter, so we converted to liters first. Now we know the dilution, the strength, 0.15 moles per liter. Again, capital M is moles per liter. What are we starting with? A 3 molar, again, moles per liter, 3 moles per liter of stock solution. And again, convert back out into milliliters. Hey, we need 0.5 milliliters of stock solution. Notice that since we're working with a volume this time, we don't necessarily have to add water back up to a certain point. We can tell exactly how much water we need. Now, it's not wrong to say add 0.5 milliliters of 3 molar stock solution and then add water back up to 10 milliliters. It's absolutely correct to say that. But unlike when we were making solutions with a salt or a solid, we know exactly how much or what volume to add. The 2 volumes will be additive. And going back to that first example we worked with, that very first question we worked with did ask for a 0.15 molar solution of lithium fluoride. Remember, in the lab, we didn't have a tool that could measure 0.039 of a gram very accurately. We can measure half of a milliliter much, much more accurately. So it'd be a lot easier to make a dilution in that case than it would be to actually just make the solution from salt and water. So the example you saw a couple of slides ago was a serial dilution, where you start with a stock solution, you dilute it once, then you dilute it a second time, then you dilute it a third time. That's a serial dilution where you're continuously making a smaller and smaller dilution. You're diluting your dilution and then diluting that dilution and then diluting the dilution solution. So here's an example. Describe the preparation of 10 milliliters of a 0.15 molar solution of lithium fluoride from a 3 molar stock solution. Here is our stipulation. You can only measure to the nearest 1 milliliter accurately. And again, this is common. This is limiting us to perhaps some real world tools. So what we're going to need in our 0.15 molar solution, 10 milliliters of 0.15 molar solution, is we're going to need 0.0015 moles of lithium fluoride. That's going to be almost impossible to measure out on a balance. In our stock solution, if I were to take 1 milliliter, again, that's the smallest measurement I can make, and our stock solution, I have 0.003 moles of lithium fluoride. And the Geico ad comes on. All right, wonderful. How about if we dilute our dilution, though? So if we take our 0.003 moles of lithium fluoride and we add 1 liter of water. Now we've arrived at our 0.0015 moles of lithium fluoride. Again, we have to think about what this is telling us. You're going to start by diluting 1 milliliter. Again, that's the smallest measurement we can take. 1 milliliter of our 0.3 or our 3.0 stock solution, and we're going to dilute it with 1 milliliter of distilled water. Now that would only get us to 0.003 moles, and we want 0.0015 moles. If we then were to add 9 milliliters to that 1 milliliter of dilution and obtain your desired 10 milliliters, you will arrive at your desired solution. You will see this formula, and I can't stop you from using it. C1V1 is equal to C2V2. The C stands for concentration. The first concentration times your first volume is equal to your second concentration times your second volume. However, it won't always work, and this is why I show you the dimensional analysis, which does always work. First of all, the C1V1 equals C2V2 always assumes that your mole 1 to mole 2 ratio is 1 to 1, and it isn't. If you're looking at a balanced chemical equation, you might have 2 moles of A and only 1 mole of B, and then the C1V1 equals C2V2 falls apart. The second assumption that it makes is that you're going from one concentration to the same concentration, from molarity to molarity, or from percentage to percentage. But you won't always be. What if you're going from a molarity to a percentage? What if you're diluting a molarity down to percentage, or vice versa, percentage into a molarity? An example of that: describe the preparation of 100 milliliters of a 4% mass to volume solution of sodium chloride from a 10% mass to volume sodium chloride solution. So again, giving us a hint here that 4% mass to volume means 4 grams for every 100 milliliters of solution. So how much of our 10% solution do we want? We want 100 total milliliters. We know that our dilution should be 4%, so here is 4 grams per 100 milliliters of solution. That's a 4% solution right there. Our stock solution is 10 grams per 100 milliliters. That's our 10% solution. So we want 40 milliliters of our 10% stock solution. And we'd, of course, then add 60 milliliters of water to make 100 milliliters of your diluted solution. So that last example, you could have used C1V1 is equal to C2V2. This particular example, you can't. It will not work. I strongly advise to get used to and good at the dimensional analysis, the factor label that I'm showing you, because that'll work no matter what your units are. So here's an example. Describe the preparation of 75 milliliters of 0.15% mass to volume sodium chloride solution from a 5.25 molar NaCl solution. So now we have the units, molar and percent. C1V1 won't work. Factor label will. We want to know what volume of our stock solution we need to make a 75 milliliter dilution. Again, our 4.15% can be written like this. Once we have grams of sodium chloride, we can go to moles of sodium chloride. And finally, here's our stock solution. 5.25 moles of sodium chloride per liter. Now you'll notice in previous steps I had just put 1 liter up here and then done the conversion from liters to milliliters. This time I'm doing that step in my head and saying 1 liter is 1,000 milliliters. So 5.25 moles per 1,000 milliliters is the same as a 5.25 molar solution. So do the math and calculate 10.1 milliliters of stock solution will be needed to make my 4.15% dilution. Another example here. If 15 milliliters of 2 molar solution is diluted to a total volume of 55 milliliters, what is the new molarity? Haha! Hey, this one's asking a different question. This time they're giving us both volumes, and they want to know what the new molarity is. So we're looking for moles over liters. That's a molarity. We have 15 milliliters of stock solution and 55 milliliters of dilution. Now notice by putting the dilution down here, I know that I'm going to want my volume of dilution down on the bottom. I'll convert my milliliters of stock to liters of stock so that I can then go to moles of stock. And then finally, I want liters of dilution on the bottom. So it's a quick 1,000 milliliters per liter. And you'll end up with 0.55 molar. Another way to do that, if you're comfortable, you're seeing the connection here. Again, the same exact problem. 15 milliliters of 2 molar solution, 55 milliliters diluted down, 0.55 molar. So homework 2.4, this is your homework for this evening. We'll take a look at this in class, hopefully, tomorrow.